discussing the carbonate platform and the different carbonate platforms we discussed except for the isolated platform. So that actually we have not discussed the isolated platform. Now today we'll start our discussion with isolated platform. Now, what is this isolated platform? This isolated platform may be in form of a, it can be a oceanic seamount, or it can be an atoll, or it can be a escarpment margin associated with fault scarp. All these they can act as a isolated platform, and these different kinds of isolated platform that basically controls the kind of the facies development pattern that we get in different isolated platform. Now I will discuss. So if I classify this, that how really is the isolated platform and how they are operating, there are two kinds. One is this and another is this. Because both seamount and atoll, they are the growth from the seafloor right within the ocean. And then how they are basically characterizing the carbonate platform. So let's start with a oceanic seamount or a atoll. That what really happens. A oceanic seamount or atoll, it basically grows right from the ocean bottom. It grows right from, so it can be a oceanic seamount Now, if this is the basin flow, and this may be a volcanic seabound or volcanic island. Now, this in the ocean water column. So, if this is the ocean surface, in the ocean water column, this seamount will cut across the CCD. There will be a CCD in the ocean water column, and they will be cutting across this CCD. So what will happen in the upper part of the CCD and in the lower part of the CCD, there will be a distinction of the different facies types. In the upper part of the CCD, you get the carbonate deposition on the surface. Carbonate deposition on the surface, and you get this carbonate, whereas below the CCD you actually do not get much of carbonate, but you can get the presence of the radiolaria chart or diatomaceous earth. That is radiolarian chart or diatomaceous earth. That is diatom bearing mudstone. Either you will get diatom bearing mudstone or you get the chart which contains the radiolaria, that is the siliceous chart. Now, what will happen in the upper part where the carbonate is growing? There you will get you will see that there are many rich people in Europe, in America. Even now there are rich people in this regime. There are rich people who are keeping money in the Swiss bank. They actually purchase different islands in the Pacific and in the Hawaii's, and they take their pleasure time there. These are nothing but this kind of situation where you have the seamount and the growth of carbonate around it and in between, because of the higher growth on the two shoulders, you get a depression in the middle of it, and where the beautiful lagoon system develop. This is a typical the seamount growth and the isolated platform. That now what will be the character of this carbonate? This carbonate normally it becomes, in many cases it become a bound stone, or it's become a packed stone. Bound stone or packed stone. Now this kind of carbonate with the internal lagoon, that is a very common association in this kind of situation. What we call, when it grows like this, we call it a atoll. The term atoll means it is a isolated carbonate platform or the isolated carbonate island within the ocean. Okay, now we will come on to the escarpment-like situation. What happens in the escarpment-like situation? This is a escarpment-like situation. You can draw it. Have you drawn it? Hello?
Yes, sir.
Okay. Now what we are showing here is a, suppose this escarpment that is formed because of any fault, or it may be a geomorphic. It may be a fault, or it may be geomorphic. Fault or geomorphic. Now, if it is a fault or a geomorphic and you develop a escarpment, in that case, what will happen? That this will be continuously coming into the effect of the waves, and that will be the failure of the escarpment. Now, you may ask me how this escarpment, the carbonate growth took place. The carbonate growth, it may be as any other, the prior carbonate platform. It may be a carbonate platform. Suppose it is a ram, it may distally stiffen ram or a rimmed shelf. Now that rimmed shelf, this has been acted upon by any kind of tectonism. So the ramp geometry is not operative now, but the ramp is now acted as a isolated escarpment because the original ramp is now tectonically disturbed. Now, if the original ramp is tectonically disturbed and it forms a escarpment, then how will be the sedimentation pattern? It will be the completely the failure of the escarpment in form of the wave activity, and that a failed sediment, either it will be in the form of carbonate breccia, or it will be the what we call the root stone or grain stone, and then finally it will be alternating with shale in the form of carbonate mass flow, where you may get what work stone. So it originally fails in the form of carbonate breccia, and then that carbonate breccia with more activity of the wave and its movement, it further the grain size get denuded and it give rise to the root stone, the grain stone, and finally the work stone. So this is a kind of the isolated platform. The two geometry I have talked about. One that is in the form of the seamount and the atoll, and the second in the form of a tectonically disturbed or geomorphically disturbed the carbonate platform, which is now becoming a source and is supplying sediment in the distal part of the basin in the form of the carbonate breccia or different kind of mass. Is it clear? Any question?
Clear, please repeat it.
Hello?
Excuse me, sir.
Yes.
Sir, please repeat the atoll part.
Yeah, atoll part, what I was discussing, that it is actually we get that in case of the isolated seamount. Now, how seamounts are formed? What in the geophysics we also discuss it as asperity or seamount. The seamounts are basically formed, that is, those who believe in the hotspot theory, they believe in the mode of the seamount. Okay? So there are oceanic islands or the seamounts. That is the elevation of the ocean bottom. That the ocean bottom always need not be a planar surface. There may be irregularities, and those irregularities in the form of the oceanic islands, and those oceanic islands which are volcanic islands actually. Any kind of oceanic volcanic island that is coming up to the sea surface. From the sea bottom, it is rising up to the now. When that kind of a sea mount is there, now you know in the ocean water column we have the chemical subdivision. We have a CCD, and above the CCD there is carbonate deposition. Below the CCD you do not have any carbonate deposition. So if you have a sea mount that is rising from the ocean bottom up to the sea surface, it will cut across that CCD. And above the CCD, you will have the formation of the carbonate. Below the CCD, you will either have the diatomaceous arc or the radiolarian chart. Now, these carbonate, they are essentially in the form of either it can be in case of the Phanerozoic, we have the huge coralline growth. Actually, what happens really? If you see, this I discussed earlier also, that if this is my sea surface, and this is the uh, uh, You can see the figure I have just drawn.
Yes, sir. Yes, sir.
Yeah. So what figure I have drawn? Suppose this is the sea level, and then up to 10 to 20 meter, you have the highest carbonate production zone where you have the highest of the illumination. Highest of the illumination, maximum availability of oxygen, provided there is very little siliciclastic supply, then you have the maximum carbonate production. And that carbonate production goes on up to 100 meter, which is the base of the fatigue zone. Okay? We know that it still continues if it is a calcitic mineralogy. And that calcitic mineralogy goes up to the CCD. That is the carbonate compensation gate. Now, if my seamount that cuts across this CCD, so I will have a active carbonate production in the top of it, and that active carbonate production, suppose in the phanerozoic, it can be in the form of coral, which is a bound stone, or it can be in the form of any kind of bioclastic rock or the ooidal rock. Not ooidal, it's the palloidal rock. That basically forms the shoulders, the carbonate production in the shoulders of the seam. In the shoulders, the growth becomes higher, and in the middle, the growth is not so high. So you generate the form of a lagoon in between. This is the typical carbonate island with a lagoon that is referred to as an atoll, which the rich people buy for their pleasure.
Okay, sir.
Is it clear? So with this discussion, actually we are completing the carbonate platform discussion. Okay, because we have already discussed ramp. We discussed both the type of ramp, the homoclinal, the distal stiffen ramp. We discussed the rimmed shell. Rimmed shell, that also we discussed. The type of sedimentation we expect in a rimmed shell, and we discussed the isolated platform, that what kind of. So if we now these are the different geometries of the carbonate. These are the different geometries of the carbonate platform. Now if I see, suppose a ramp. Now in a ramp, it can be a tide dominated, it can be a wave dominated. Okay. So if it is a tide dominated, the ramp will be of low energy. Whereas a wave dominated ramp, that will be more higher energy. Okay? So this is true because tide is a low energy environment. Now, any ramp that is subdivided into, whenever we should do the field work, we try to understand the kind of geometry of the ramp, that what kind of sediment I expect, the different parts of the ramp, and why the different kind of manifestation of this different type. So we divide the ramp into three parts actually: inner ramp, mid ramp, and outer ramp. What I am saying, that any ramp is further divided into number one, inner ramp. What is inner ramp? Which is most proximal to the continental side. Okay. Then mid ramp, and then distal. What I am talking about is irrespective of platform geometry. Irrespective of platform geometry, whether it is a homoclinal, distal stiffen, then ring shell, isolated. Actually, when you see it in the, because all these geometries, try to understand my point. All these geometries that is visible in the modern ocean. But in the rock record, when you are identifying the carbonate and trying to decipher what was the carbonate platform geometry during the Paleozoic, during the Mesozoic, during the Precambrian, when I am seeing a carbonate succession. How really we do it? It is not very easy that in a Paleozoic succession, a carbonate succession, that will show you that यहाँ पर लेगून था, यहाँ पर जो है reef था, यहाँ पर isolated CCD, Yeah, nobody will tell you. This is all theoretical based on the modern observation. What we have to do when we do it in the geological past? Suppose you are, as a geologist, you are in an oil company, and the oil company has hit hydrocarbon in a carbonate succession of the suppose EOC, and that is in the subsurface. Now, you are, as a geologist, you are asked to what was the carbonate platform geometry, how the facies variation I am expecting in the subsurface, which portion of the carbonate platform I will be drilling for hydrocarbon, which portion I will be not drilling, which portion I expect the maximum concentration of the hydrocarbon, how the secondary porosity is developed in the carbonate platform, where the secondary porosity will be maximum, how it is controlling the permeability. All these questions will be asked to you as a geologist when an oil company will heat the hydrocarbon in the carbonate in the subsurface. Then what will you do? Nobody will show you that yes, there is a escarpment, there is a atoll, there is a homoclidal lap. So theoretical hai na? All these things I am discussing based on the modern observation and the theoretical. Do you agree with me what I am saying? Hello?
Yes, sir.
Hello? Yes. Try to understand the complexity of the matter. Try to understand the complexity. बाद में नौकरी करने जाओगे और मेरे को गाली दोगे, सर ने तो कुछ बोला ही नहीं. तो प्रॉब्लम ये है कि actually when we go to the geological record, all this geometry is not visible, but it has to be reconstructed. And reconstructed, how it is reconstructed? It is reconstructed based on the facies type what we get in the rock. So we identify the different carbonate facies, we identify the process involved in the production of that facies, we identify the facies association, and then we try to assign the facies association in a particular geomorphic setting of a carbonate plane. Now, for that, because if I make that very complex, it will be very difficult to do it. We basically, and in that case, we minimize our complexity and we try to streamline our discussion based on the simple products of the carbonate ramp. And we divide it into inner ramp, mid ramp, and distal. That what kind of the basis I expect in the inner ramp, mid ramp, and the outer ramp. So that we can at least talk to the authority that yes, this is the kind of facies I am getting. So this is the inner ramp. So from this side to this side, the ramp is actually getting higher bathymetry. You are going to the more distal part of the ramp, and here this kind of facies I will get. So if you want to have hydrocarbon, there is more possibility that this side is more prospective than that side. Okay, and so inner ramp. What is the inner ramp? Suppose a tide dominated setting. Then what I will expect in the inner ramp? I will have tidal channel, and there will be the flat plane. So tidal channel will have the more coarser grain carbonate than the flat plane where there will be carbonate mud. So I will expect grainstone in the channels, tidal channels. I will expect the carbonate mudstone or micritic limestone in the flat. Okay. Then if it is a wave dominant, then what I will get? I may get the cross-stratified carbonate. I may get the stromatolitic carbonate. I may get the all these types of carbonate that I may expect that there is a more action, the cross-stratification, large-scale cross-stratification, chevron cross-stratification, trough cross-stratification, all in the carbonate. I'm saying all in the carbonate because wave is acting on the carbonate. And then those cross-stratifications that talk to you about the higher energy, relatively higher energy of the wave domination. Okay. In some cases, what I can get that the development of the shoal, 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 What in the siliciclastic we call bar, in the carbonate we call it shoal. So there can be carbonate shoals in the mid-ramp. We can have the development of the carbonate shoals. It can be bioclastic shoal, it can be void shoal. Bioclastic shoal or void shoal. Okay? And if the shoal is formed, at the back of it, you can have the carbonate mudstone, which can be the lagoon kind of situation. Then coming on to the distal ramp, if you have a ramp slope margin, there is development of a reef structure. And if you do not have a reef structure, then the total basis pattern will be different in the distal. If you do not have a reef structure at the reef, at the self slope break, in that case, you will be getting the carbonate mudstone with rare supply of the carbonate grainstone. But if you have a reef development at the self slope, then reef will totally control the phase distribution at the back of it. It will generate a huge lagoon and it will supply the reef derived talus into that. Reef derived talus. Any question, or should I tell you in a diagrammatically form?
So please explain mid-ramp again.
Okay. So if I have, suppose I am drawing a carbonate ramp. I am dividing it into inner, mid, outer. Now this ramp may generate a reef at the end of it, or it may not generate a reef. Both the possibilities are there. Now in inner, I am dividing it into a tide dominated, a wave dominated. In case of tide, I can have a tidal channel or floodplain. What I expect in channel? Grainstone, carbonate grainstone. What I expect in floodplain? The micritic carbonate. If you have a wave, how you identify that? That is the cross stratifications, which can be trough, planar curved, all this cross stratification. You also can have the plain laminated curve. Okay, and all these you can also have the chevron cross stratification. All these indicates the mode predominance of the wave. Okay, then I may have the presence of, these are shoals. Shoals. The shoals in the mid ramp. Shoals can be either bioclastic or it can be voidal. Voidal shoals. Now these shoals, they may be reworked by the wave and can supply sediment both this side and this side. On both the side, the voids can be distributed, or the bioclast they can be distributed because of the reworking by the wave. You can also have the formation of the patch reef, which are isolated biothermal structure. Isolated biothermal structure. And otherwise, this portion is laminated limestone. Laminated limestone. In case of Precambrian, we call it cryptalgal limestone. Cryptalgal limestone. The algae they form it. In case of Phanerozoic, these cryptalgal lamines are less. You get the normal micritic limestone. In Precambrian. Precambrian we call it crypton in Precambrian. Crypton. Then you get the development of the reef. If reef is developed, then the entire pattern becomes different because it becomes a energy shadow. And then the very low energy environment that basically operates, except some reef derived talus that may be developed. Reef derived talus on both sides, the reef derived talus. Or if the reef is not developed, in that case, you may get some thin bedded carbonate alternating with shale. Is it okay?
Yes, sir. Thank you.
Okay. Actually, carbonate is a very fascinating and problem in carbonate is different. In case of siliciclastic, you can easily identify the proximal distal relationship based on the energy, relative energy at different places. Because we know that if we go from the continent to the ocean side, that the relative energy of the system will decrease. So we will get the scale of bed form will decrease, degree of amalgamation will decrease, the storm energy, that means the amplitude of the bed form will decrease. All these things that forms a very systematic pattern from proximal. In carbonate, this systematic pattern gets totally disturbed by means of the biotic role. The biota, it creates a havoc in the case of carbonate because it can generate a shoal, it can generate a reef at any place in a carbonate and can totally change the gaseous distribution pattern, totally change that what energy will create at what place. That is a huge problem. Now a reef, it is not always that the reef will always form at the self-slope break. Though majority of the reef, they form in the self-slope break. There can be mid-ramp reef also, mid-ramp shoal or reef also. And in that case, the entire situation in the mid-ramp itself, it changes. So that's become a huge problem for the, first of all, in the ancient succession to reconstruct a carbonate platform geometry, as well as when you are working in a subsurface strata, particularly for the hydrocarbon exploration, then it also becomes a huge problem. That how to identify the taste of the carbonate reservoir zone we need. So what people normally do, they try to have very high resolution subsurface seismic data. High resolution. Where the resolution level, unless is high, then because carbonate is so unpredictable in terms of its porosity permeability. Even within the, I have seen from the Gulf, there was a project with me from Slumberger, where they provided me the, they have taken away all the samples, but if I search, I will have the photographs that I have taken. It is a hydrocarbon delivering system, and they actually wanted from me to identify the amount of porosity available at different stratigraphic levels. So I have seen that within a few meters, that drastically the porosity level changes in the carbon. Drastically. Within a succession, there is a micritic limestone at certain level, but suddenly it becomes a bioclastic limestone. And as it becomes bioclastic limestone, the intraclastic or interclastic porosity that extremely become high. But when it is a completely micritic, the porosity level is low, and that is very, very close to one another. It is not that that you measure one porosity and that will be continuing for a significant distance. No. There are different kind of porosity, and the one major role in carbonate that is a intraparticle porosity, which was not there in the silicic cluster. You see, whenever you have a huge bioplastic limestone, there is a huge contribution of porosity by the intraplastic porosity. Okay. So with this, we end the carbonate discussion. Okay, because we have discussed the carbonate formation, carbonate diagenesis, carbonate platform with this. Now, our next topic is dolomite. Dolomite. Now, dolomite, which has a composition CaMgCO3 hold. Okay, and this dolomite, if you see that first described in about 200 years back, the Donald D. Dolomitou. His name was Donald D. Dolomitou. He first described the dolomitic rock from the Alps. From that time onwards, the dolomite is known to people. And if we see the distribution of dolomite right from the Precambrian to the Holocene, every time, wherever carbonate rock, you get the dolomitization. Now, dolomite is a mineral. So, what is the rock where I get the dolomite? That is dolostone. But we always refer dolomite. So, there is a misnomer in it. Despite dolomite being a mineral, we always refer the rock as a dolomite, which is not correct actually. You could understand what I am telling.
Yes, sir.
So ideally it should be called dolostone. Dolomite is a mineral. Now, how dolomites are formed? Where dolomites are formed? All these are questions. And why dolomite is so prevalent in the rock record? So, there are two major theories. One, some people believe that dolomite is inorganically precipitated. Another school, they believe, no, it is not inorganically precipitated, but dolomites are replacement product of carbonate. And third theory, that is, they say, no, dolomite is a penny-contemporaneous replacement of carbonate. Penny-contemporaneous replacement of carbonate. We will discuss what are the merits and demerits of these different claims. First, start with inorganic precipitation. That many people said, no, the dolomites so prevalent, they are basically precipitated from the water. Now, you see, those people who are objecting to it, what is their major argument? They say that dolomite is a extremely ordered structure, where 50% of the cation is represented by calcium and 50% by magnesium. Okay? So 50% by calcium and 50% by magnesium. And this is a very stoichiometric distribution. This is a very stoichiometric distribution. If you see the dolomite under thin section, you can see that is the beautiful rhombic structure of the dolomite. Beautiful rhombic structure of the dolomite. And that rhombic structure, the beautiful crystallographic phase development, that basically talks about the extreme stoichiometric structure of the dolomite. Just 1 minute. So, বন্ধু আমি একটা ক্লাসে আছি, আমি একটু পরে না আমি তো ক্লাসে আছি। So now, if people try to crystallize dolomite from the water, and what they say that the normal pressure temperature condition of the ocean water, that is 25 degrees centigrade and 1 atmosphere. 25 degrees centigrade and 1 atmosphere pressure. This condition, 25 degrees centigrade and 1 atmosphere pressure. In this condition, we do not get any dolomite formation, because for formation of such a stoichiometric structure where 50% cations will be occupied by calcium and 50% by magnesium, that requires a very high degree of kinetics, and that kinetics cannot be attained at this normal pressure temperature condition of the ocean water. In fact, they have observed that it cannot be you cannot have that kinetics unless you at least have 60 degrees centigrade temperature of the ocean water. And the best possibility of having this is about 100 degrees centigrade temperature of the ocean water. Below 60 degrees, such stoichiometric structure cannot be. So how can the ocean have such a high temperature so that it can facilitate the inorganic precipitation of the dolomite? Okay? Inorganic precipitation of the dolomite. Is it clear?
Yes, sir.
Okay. They also say that many of the dolomites, they are showing textures which are similar to carbonate, That means in many dolomites we get void, many dolomites we get bioclast, many dolomites we get the pelloid. If the same structure is shared by both carbonate and the dolomite, then why not to support the replacement of the carbonate by a dolomitic solution? Rather than inorganically precipitating dolomite from the water column, they say that it is better that if we propose that the secondary replacement of the carbonate by a dolomitic solution. That is this. Because on one hand, they have shown that inorganic precipitation is very difficult unless you have a very high temperature of the water column. At the same time, they say that presence of different textures which are commonly observed in the carbonate that is available in the dolomite. So this second school of thought, they started propagating, so it is actually a secondary replacement of the carbonate by dolomitic solution. Okay. Now, this group is very strong, and they try to say that the secondary replacement of the carbonate, that is the major reason. Then there is another third group. They say, okay, we understand your logic. There is secondary alteration, but in that case, the dolomite crystal should be large size, in average large size. You are replacing it and giving it enough time, so we expect the coarse grain dolomite to be formed. What about the very fine grain dolomite, which are observed in different parts of the world? Very fine grain dolomites, extremely fine grain dolomites, and those fine grain dolomites, they lack any kind of carbonate texture. So then the third proposal that came, they actually didn't believe the total replacement, the secondary post-depositional replacement of carbonate. Suppose a carbonate is formed in the Paleozoic and that carbonate is exposed to a dolomitic solution in the Mesozoic, then the dolomitic solution is making the carbonate dolomite. They actually do not believe that. They say no, in that case all the dolomites should have been coarse grained dolomite. What about the fine grained dolomite? They actually name those dolomites as proto-dolomite. Then they say, yes, we also are believer of replacement, but the replacements are peri-contemporaneous replacement. That means when the carbonate is depositing, at that same time the dolomitic solution is replacing it. So carbonate deposition and dolomitization, they are going hand in hand. Am I clear? So there are three proposals. One, carbonate precipitating from water column, which is largely discredited. Dolomite precipitating from water column, which is largely discredited. Then the secondary replacement of the carbonate, which there was a strong group, and there is a third group who they say no, there may be replacement, but the replacement has to be peri-contemporaneous. That means carbonate and dolomite, they are going hand in hand. Carbonate is precipitating and immediately getting dolomite. And that's why the fine grain nature is present. Am I clear?
Yes, sir.
Okay. So accordingly, there are three different models that is proposed for the dolomite. I will discuss now those models, that how these three different logics that people try to explain that yes, this is the reason that dolomites are formed. So the three different situations. Now it is coming to the normal natural situation. In natural situation where this kind of situation, that is dolomitic solution is forming and carbonate is also forming, they are replacing, in this situation where it can arise. So three different model. One is Sapka model. Or what we call the hypersaline model. Number two is schizohaline model. Schizohaline model, which is also referred to as the Dorag model. And number 3, shallow subtidal. Okay. So there are 3 different kinds of models to explain that how dolomites that is forming, and what is the necessity of 3 different models. First, so I first give you a very simplified picture of the 3. Can you see the figures?
Yes, sir.
Okay. Please let me know when it is complete. So finally, I took a new laptop for taking class because there was a huge problem. I could not take class.
So in the down diagram, that seepage reflex is written.
Huh?
So in the last diagram, seepage
Ah,
reflex.
seepage reflux. Seepage reflux. This is capillary drawdown. I will explain. Seepage reflux, capillary drawdown. Okay, I think you people have drawn. In the top, I am showing the three different situations which I will be discussing now. The first, which was drawn, that is in a larger scale, drawn below. The first one, which is the hypersaline, this is shown below in a large scale. Now, this model is described from the Persian Gulf in the Sabka condition, where there are formation of evaporites also. So what they say, that if you have this kind of a situation and a lagunal condition, so there is evaporation. And because of evaporation, the more and more water that is in the subsurface, that is being capillary, through capillary it is going up and getting evaporated. Okay, and that basically will cause the formation of dolomitic solution, evaporite and dolomitic solution. Now, what is a dolomitic solution? How I characterize a dolomitic solution? A dolomitic solution should have high Mg by Ca ratio, and it should have a low Ca by CO3 ratio. Right? The Mg is to Ca ratio, it should be from 5:1 to 10:1. Am I clear? What is a dolomitic solution? A dolomitic solution किसको बोलेंगे? Where you will have a high Mg by Ca, low Ca by CO3, and Mg is to Ca ratio is 5:1 to 10:1. That is what they were in this model. They say that is a dolomitic solution. Okay, and once this solution, because of the evaporite and the increase in the Mg is to Ca ratio in the water, and it become denser. Because of evaporation, the water become denser. So the denser water that will sink and sink to the towards the sea direction, because that is the base level. So the water, the denser water, the lighter water through capillary drawdown, it is lifting, getting evaporated, become denser and sinking and moving towards the ocean. And in this process, in the way, it will be dolomitizing the carbon. That is the model. That is this model, which is a hypersaline model. And the dolomitic solution will have the high Mg-Ca ratio, low CaCO3, high Mg/C. I think you could get my sense.
Yes, sir.
Yes, sir.
Okay. Now, this model was okay with some people, but not okay with many people. What they say is that on one hand you are saying that for dolomite formation you require higher kinetics, and when I will have higher kinetics, a more dense solution or less dense solution, less dense solution. Definitely, when that solution density is very low, then you will have a higher kinetics and higher development of the. But what you are doing here, you are generating a denser solution. How can a denser solution promote the dolomite? Is it clear? What was the main objection?
Yes, sir.
And also, many of them documented that they are getting dolomite without any association of evaporite. Because in this model, you are always saying there will be evaporation and associated the dolomitic solution. Is it true always? No, because we are not getting evaporite in association, but we are getting dolomite. So how can you say that there has to be a evaporation, the denser formation, and then the sinking of the water and that will come? So they didn't agree. And who are those? They are mainly from Australia. They are mainly from Australia. And they showed there is a series of sea ponds, what they call kudung, 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 K-O-O-R-O-N-G, kudung. Some say K, some say C. These are nothing but a series of sea ponds in Australia where there is extensive dolomitization without any evaporation. So this model came, schizohalite. What they say that we have a dolomitic, they countered this definition of dolomitic solution. They countered this definition of dolomitic solution. They say a dolomitic solution should have Mg is to Ca ratio 1:1 to 10:1, and it should have a low salinity. That is their view, schizohalite. They say even I can have a dolomite with Mg is to Ca ratio 1:1. They actually claim that. You need not have a Mg is to Ca ratio 5:1 to 10:1. You can also have a dolomite with Mg is to Ca ratio 1:1. That they say, provided salinity remains low. You are increasing salinity and then saying you require higher Mg is to Ca. And what they say, then they say how they achieve that. They say mixing of meteoric water with seawater. That is there. Mixing of meteoric water with seawater. What they give this model. So, you participate. Please let me know when you will drawing the picture.
Excuse me, sir.
Sir. Hello, sir.
Excuse me, sir.
Is it done?
So the x-axis is not visible.
Uh, ऊपर का
Yes, sir.
now.
Yes, sir.
You will get this picture in Sampok's book also. Now, what is actually they are trying to show by this picture? They are saying that they want to keep the salinity low, and they are saying that even if they have a salinity that is Mg is to Ca ratio 1:1, that means low salinity, then also if low salinity, suppose salinity 0.01, 0.1% or 0.003%, then also you can have dolomite, provided the salinity low and they are getting that the dolomite, the aragonite and high Mg calcite, that will be replaced by dolomite. That is they are saying that the dolomite field, it is not only dependent on the high density and the sinking. Even I can have, if I have a mixing of the meteoric water and the sea water and the decreasing the salinity. So their main thrust is decreasing the salinity. Decreasing the salinity will promote the dolomitization even at a lower Mg to Ca ratio. That is what they were trying to tell. Okay. Now, is it clear from this picture and whatever I have said? Is it clear? Whatever I want to tell.
Yes, sir.
Now, those who used to believe in the first proposition, one major person, his name is Hardy. Hardy. H-A-R-D-I. Hardy. He was very reluctant in believing this model. He said the experiment what these people have done by means of the dolomitizing solution and lower salinity, that they did with a dolomite which is not stoichiometric, but it is a calcium rich dolomite where the magnesium is 30 to 40%. 30 to 40%. They have not taken a dolomite which has a 50% Mg. So what Hardy said, that this model has a lacuna because the model has been experimental with a impure dolomite with a more calcium content. This figure is a experimental figure. You understand? This is the experimental figure where different salinity and different Mg is to Ca ratio and a proper carbonate saturation level has been provided in the experiment, and the different phase development has been seen. Now this experiment has been done with dolomite, which is a calcium rich impure dolomite. That is, they have said. So because it is a impure dolomite, the results of this experiment may not be sacrosanct. That is what they say. So I have discussed two models and the arguments against the validity of those models. One is the hypersaline model with the argument, and the this model, your schizohaline model and the argument against. Now there is a third model, which is a shallow subtidal model. What it says that the dolomitization by normal seawater, there is no salinity decrease, no salinity increase. Because one model talked to you about the salinity increase, the other model talked to salinity decrease. In one model, you are mixing the meteoric water. In other model, you are evaporating the seawater to make it dense. Two different extremes. Now a third model has come, which talks about the shallow subtidal model. Shallow subtidal model. Okay? Shallow subtidal model. Now, this shallow subtidal model, in that model, what is said? That I have a carbonate succession and it is continuously being pumped by seawater. Suppose you have a reef, coral reef. Think of the Great Barrier Reef of Australia. And continuously the seawater is coming and it is striking the reef. So through the different porosity system and with permeability, the seawater is continuously getting replenished through the entire body of this carbonate. Entire body of the carbonate, the seawater is continuously getting replenished. And normal seawater has a Mg is to Ca ratio 5:1. You need not have to decrease or increase it. You need not have to take to 10:1 or decrease to 1:1. You just have the normal seawater. And normal seawater, it has a high Mg is to Ca ratio. Now problem, where lies the problem? Problem is that at low temperature, magnesium has a high tendency to combine itself with H2O to form MgOH2. So normally magnesium will not try to enter into dolomite structure. It has a general tendency to combine with H2O and form MgOH2. So in normal temperature, the dolomite that will be forming, that will be impure dolomite with more calcium entering into the structure. So that will be more impure dolomite with high calcium content. But if you can increase the temperature at least up to 40-45 degree, then this OH that get detached from Mg, and more mg. So what is shown is that in most of the cases, the shallow subtidal, this model become more valid in the tropical region where you have a high temperature attainment and the magnesium gets the chance to get free from water molecule. And the continuously it is getting replenished within the body of the carbonate, and for a long residence time. I am also harping on, there is a long residence time. Long residence time that basically help in the dolomitization of the carbonate. So what I have said, that a continuous pumping of the seawater into the carbonate body, the deep invasion of the ocean water within the carbonate, and with this porosity, permeability, and the long residence time. All these three together with this original mg to Ca ratio 5:1, and at temperature attaining about 40-45 degrees, it is common in case of the tropical condition or subtropical condition. There, this condition may give you a possible dolomitization of the carbon. All right, clear?
Yes, sir.
Okay. So we have discussed, initially we discussed what is the problem in inorganic precipitation of dolomite, what is the replacement theory of the dolomite, and what is their logic, what is penicontemporaneous dolomite. Then we discussed at what natural condition these different conditions can achieve. One is a higher density, another is a lower density, and another is a normal sewer. And how these three different kind of condition. Now, question is that when you will be working in a dolomitic country, and then somebody asks how this dolomitization took place, then which model you will believe? I am not asking you to believe any one model or the other model. All the models that will be believed depending upon the local geological condition. What are the different other associated rock types and materials you are getting in association? If I get evaporite in association, my interpretation will be more biased towards hypersaline. If I don't get evaporite in association and we are getting the large number of the carbonate texture within it, then I will be going to the more schizohalite, or I will go to the channels. Okay. I think it is now clear what is the major dolomite problem. This is what is called the dolomite problem. This is what is called the dolomite problem. And you could understand that what is the problem of getting. One major way of identifying dolomite in the field, what is called the, how we identify dolomite in field. There is a very, very significant structure. By seeing that, we can see it is dolomite. What is that called? Do you have idea? Hello? Hello?
Yes, sir.
Do you have idea that in field, if I see that structure, then it is very easy to tell that yes, this portion is dolomitized and we are getting. That is called chopping mark. Chopping mark. Chopping mark. Chopping. Some people also say elephant skin structure. Elephant skin structure. It is something like that you have seen if you go to any kind of I do not know how many of you are non-veg. Those who are non-veg, if they go to the to the mutton shop, the person, the way that person chops the mutton, something like that, the rock is chopped. Rock is chopped. It is, and we see that the skin of the elephant. There are big chopping marks on the skin of the elephant. So that, like that, we get that kind of mark on the surface of a dolomite. Okay. So we'll stop here today, because if I start the evaporite today, time is not there. So tomorrow we'll discuss evaporite, and if time permits, phosphorus. Okay.
Okay, sir.
Okay. And we'll have a practical today at 2:30. Is Aditi online?
Yes, sir.
So there we'll have a practice 2:30. I will come back.
Okay.
Okay. So for if there is any question, you can ask afterwards also. Thank you.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.